Hi, good morning, everyone. Thanks for coming. This is Xin from Microsoft. Joining me, I have Guohan from also Microsoft, Ben from Broadcom. We are here to present the SONiC community work in the last year. We are going to cover three topics, three aspects of the project. One is reliability, warm reboot, how to help you to achieve the high availability. Second one is what we are going to do and what we are building in terms of management framework. The third one is we are going to show you examples how easy you can extend the solutions to cover new scenarios. So before we start, I will give you a very, very quick recap of the SONiC so that you can enjoy the rest of the talk. Basically, it's OS built for all the switches. It's built on top of Linux. Second, because of we are using SI, it's an interface to abstract all the SDK communication to the NORs, so it enables us to build the NORs that is agnostic to the platform. We containerize all the component to be using a Docker container, so it enables us to choose the component that we like or easily to extend the OS to your scenarios. Also, we are leverage the rich Linux container, Docker, Kubernetes management ecosystem, so you can pick your management tools. So in the last 4 years, it has been evolving very fast. Just a very quick cap. We start with a very basic functionality L2, L3 functionality with a very good solid bounds container architect with Redis DB. And the next year, we start to build more advanced features like RDMA, IPv6, management through Swarm. In the third year, 2018, we spent effort in beefing up streaming telemetries, config.db to enable later we are able to build REST API management on top of it. In 2019, we have been spending a lot of effort on building advanced management framework, which Ben will cover, and as well as systematically improve the development experience, test experience, as well as higher, richer features. From the ASIC and platform point of view, we evolved from the very beginning only in 5 platforms and 40 gig, a few ASICs, to now we have 92 platforms, include all the latest advanced chipsets supporting SI and supporting SONiC. The scenarios we covered from the very basic of data center leaf tool to be able to support bare metal service, gaming service, AI service, which has very high requirement of reliability, fault tolerance. From the community point of view, we start with a few very core companies supporting that. We have more adopters, as well as people like companies start to provide commercial support, deployment solutions, a whole set of solutions. So in the community, we appreciate the members that stay with us. We see a lot of familiar faces like Broadcom, Dell, Mellanox, MetaSwitch was there also from the very beginning, also EdgeCore. We also welcome new members. Each year we continuously add new members like Juniper, Rijie, MyTech, and Alpha from the hardware point of view, Baidu, Didi Taxi, Jingdong Cloud from the user point of view, as well as we have research company, we have service company, xCloud, Avis, all joined the community since last year. With that, I'm going to give time to Guohan to talk about the first aspect, how we are going to do to help people to reach a higher reliability.
So today I'm going to talk about the first topic is using the warm boot to solve these high reliability issues. So in our network, all the servers are connecting to a single Tor, and from that Tor, then you connect to the leaf nodes and spine nodes. You can have redundancies on your leaf nodes and spine nodes, but you cannot have in our architecture, you do not have a redundancy in the Tor nodes. All the servers only connect to a single Tor. If the Tor fails, then all the servers looks the connectivity. So most important things for us to solve is that we want to have this highly reliable network. Then we do not have a instance that impacts the customer for networking. And this effort is a truly community effort. We have, this picture was taken from integration event that we have from multiple cloud providers and also from multiple device vendors, ASIC vendors, so that we can have an end-to-end stack of integration to provide the solutions. So before I talk about warm reboot, let me explain some of the concept here. So first is a fast reboot. So in this case, so for both warm reboot and fast reboot, the idea is that we completely reboot the whole box. That the control plane is done, we reboot the box, we reboot the Linux, and then during that period of time, we do not want to lose the data plane. The data plane is still functional, forwarding the traffic for the customer. And the first idea is the easier idea we did is for the fast reboot. In this case, we first start the OS reboot with the Linux command kexec. At that moment, you see the control plane is disrupted. But we make sure that the control plane is coming back within 90 seconds so that there's some control plane probe like lag and the BGP. The neighbor will not lose the connectivity so that the neighbor will still think the Tor is still there. And then after the control plane boots up, then it starts a data plane reset. So during this moment, we reset the ASIC chips so that the ASIC stop forwarding the packet for a moment for a period of time, which is less than 30 seconds. Then after the ASIC is reset, then it's coming back. We learned all the routes from the peers, and then the box starting forwarding the traffic again. In this case, we completely upgrade the whole box with a new. We can upgrade with a new kernel, new SDKs, and then the data plane downtime is for 30 seconds. So this is our first iteration to improve our customer experience. Then we went to another iteration, which is much better, because in this case, as you can see, the data plane disruption time is the same. The control plane disruption time is the same as the fast reboot, but the data plane disrupt time is only less than 1 second. So there are a lot of engineering work that go into the second warm reboot. So what happens is that so we have in our system architecture, we have applications sits on top of the database. It writes all the routing interests, the neighbor interests, all the networking state into application DB. And then we have an org agent that computes all those routes and neighbors and translates into a side object. And then after that, after all the object put into we call the ASIC DB, then there is a syncd process that syncing all those objects into the ASIC. So the warm boot works first is that before we do the warm reboot, we store all the application and the ASIC DB contents onto the disk. So we processed all those states in the network onto the disk first, and then we do the boot. Then we reboot the box. At this time, the data plane is not disrupted at all. After it boots, the first is that the Redis database reads the content from the disk and restore all the application and the ASIC DBs. And then the org agent reads the application DB and compiles a new ASIC DB. You can think like the occasion is the compiler for the application DB and compiles a new ASIC DB. And then, because in order, when we want to do the warm boot, we either add features or fix bugs. Maybe the bug in the occasion, but in the previous case, maybe the application DB, they take the application DB and compile some wrong entries in ASIC DB. And we want to fix a bug by upgrading occasion, by rebooting with a new image. So in this case, the occasion reads the application DB and recompiles the ASIC DB. And then we do the syncd part is comparing the old and new ASIC DB. So you can imagine there are tens of thousands of objects, and the syncd compares them one by one and find out the match. If there's no match, then it tries to create new entries. If there's some old entries, you try to delete those entries. So after that, then the application wakes up. The application then talk to the neighbors and learn new state and put the new state into application DB, and on occasion we read the new state and sync new state into the ASIC. So as you can see, this is a very a little bit complex process. So that's why we need the end-to-end integrations with application with a site to make this work. And there's one more thing here. So for the networking protocols, we have a BGP, lag. Those have graceful restart feature that is embedded in the network. However, we're talking about the Tor, and we care about the servers. So what about if the server is continuously doing the ARPing the gateway address for your Tor? What if the Tor is going away, the control plane is going away, you are not responding to the ARP? During that moment, how are we going to handle this availability issues? So what we come up is that we come up with the idea of control plane assistant. This is a new feature that we haven't been seeing in any of the NORS vendors, existing NORS vendors. What it does is that traditionally, the server sends you ARP request, and your Tor responds with ARP reply. This is on the condition that your Tor, your control plane is alive. However, if your control plane is going away because you reboot your Linux, then what happens is that when the Tor receives the ARP request, on the data plane, it encapsulates the ARP request with a new header, and then forward the ARP request to a remote node, which we call a control plane assistant. This is purely done in the data plane, in the ASIC on the Tor. And then the control plane assistant knows its Tor and knows its neighbor address because it does a sync with the Tor. So it does a reply, send to the Tor, and then the Tor decaptures the packet, and then send the ARP reply to the server. To the server, it looks like it just received a new ARP reply. It doesn't care whether it's really coming from the Tor or coming from the remote, because it cannot distinguish. It's the same ARP reply that's sent by the Tor. So in this case, even the Tor's control plane is going away, the server can still successfully doing the ARP with the Tor. So it will not losing its default gateways. So this also addresses many, whether you are Linux or Windows, you have this periodical ARP refreshing. So then in this way, we can complete the picture. We reboot our NORS in our network every day, and then the customer would not notice any disruption. Okay.
Do I have to do anything to turn this on? Okay. So Ben Gale, Broadcom, software architecture team. So Broadcom's been involved in SONiC for a number of years now, but mostly on the site and on the platform side. But we've long since recognized the importance to the industry of having a good open source NOS. And we've watched with interest as SONiC has grown and matured and gained traction in the industry. And so this year we've done a lot more investment on the protocol, on the application side, to extend that success for SONiC, and also to bring it to other use cases beyond the kind of the web scale DC operator that you mostly see SONiC deployed in today. So to that end, we've done a lot of work around starting to contribute new features into SONiC. I'm not going to go through this whole list there. You can see it on the slide. It's also starting to appear in the GitHub, so you can go see it. Our topic today is what is the stuff in red, which is this thing called the management framework, and providing a new management interface into SONiC. And this has been done as a joint effort, kind of joint development with Dell. So it's been a nice example of community. So what's the problem we were trying to solve? We wanted to provide a more integrated and OEM-like management experience to the end users. When I say integrated, if you look at SONiC today, the UI is somewhat fragmented. You do some of it in the Linux shell, you do some of it in the SONiC CLI, you do some of it through application CLIs like FRR for routing or TeamD for lag. You have to go to all these different places to kind of do what you want to do. And what we wanted to do was provide something that was more integrated into a single user interface and gave a much more OEM-like experience to the end user. We also wanted to provide more standards-based programmatic interfaces, such as GNMI on OpenConfig and RESTconf, using standard Yang modeling. OEM-style AAA and security, and then extend and add broad feature coverage into this UI so that we get that fully integrated experience. So what have we been doing to fulfill that requirement? There's really two things. Firstly, we've created a framework to allow ease of development of these user interfaces into SONiC. We recognized that we had to make it as easy and as fast as possible for developers to provide those UIs in order to get the feature coverage that we wanted to see. And we've also started the process of filling out that UI content with contributions of our own into that user interface for SONiC. This is like a simplification of what we've done. We don't have nearly enough time today to go into the detail. In essence, there's a new Docker in SONiC, which is providing this management framework. The heart of it is this thing called the translib, which provides the transforms between the north-facing exposure of management, which is normally kind of JSON encodings into some kind of protocol, standards-based, and the southbound, which is the interactions into the SONiC primitives. Now, most of that happens in databases in the SONiC world, be it the config DB or state DB or counters DB. And then once you put it into those databases, everything else in the control plane and down to the hardware kind of happens under the covers. And what we tried to do is make it so that it was as easy as possible for the developer. On this particular slide, the idea is that the stuff in, without the shading, the stuff in white is the common framework and auto-generated code. Which the user or the developer does not have to write code for. It just happens at build time or as part of the common framework. The stuff in blue is the input that the developer has to make to provide the UI for his new feature. And as what you'll see from this is a lot of this happens through data modeling, right, rather than writing coding, and we auto-generate from there. So as an example, typically when you add a new feature, into SONiC, you will create a schema for the databases that will support that feature, and that will be like the southbound of the translib and this framework. So typically, a developer will start by expressing that in what we're calling SONiC Yang, and it's standard Yang, but we've written some guidelines that refine how you address that to this specific use case. And then that SONiC Yang is then used by the framework to do all the validation, so that we know that when we write things into the database, that they are validated before they go in there, and we know it's going to work. And similarly on the read side, you can also use that as your northbound-facing interface. But our preference really is that we use the standard Yang, mostly OpenConfig, as the northbound for SONiC. And that means that end users who pick this up can use existing tooling they may have in place, using kind of OpenConfig, IETF, IEEE data modeling techniques. Now, in the case of where your standard Yang maps closely onto your SONiC Yang object, that code can be auto-generated. The developer does not need to do anything, and we've provided all that in the developer workflow in the framework. There are, of course, cases where that isn't the case, and that the semantics of the objects in the standard Yang world are different from those in the SONiC expression, and so they will have to write some code for those. In addition, you can do platform modeling, so that you can use the same code on different platforms which may have different scale and different capabilities, but you can provide per platform modeling so that the validations can take that into account at runtime. Once you've done all that, you then have a GNMI service. You have a RESTconf service, and your client code can just come along and just use that, and it all pops out of the build process. In addition, you have the CLI, and this is the industry standard look and feel that we were trying to get. We are using something called CLISH, which is another open source project for providing industry standard CLI modeling. You use XML as the expression language to define the command tree, and then you use actioner and renderer scripts to actually implement the details of that, again adapting onto the translib and the SDK services that we provide to interface to that. That was kind of a very brief description of something that is, obviously we could spend an hour on this topic. If you want to learn more, what have we actually done with all this? So in the 2019-10 community release for SONiC, you will see the framework there. This code is being contributed now. The design specs are out there. We're also providing developer training and guidelines on how to develop in this environment. We've defined the guidelines, as I said, for writing SONiC Yang, which is standard Yang, but just refined for this particular purpose. And we've also provided, again, along with Dell, some feature implementations that use this framework to expose some standards-based programmatic interfaces for open config features such as interfaces, LLDP, system, platform, and ACL. And then we provided supporting industry standard CLI for all that stuff. And you get RESTconf as well. This is just the tip of the iceberg. It's just the start of the journey. The idea is that we put this stuff in there. We provide implementations for both user and for developer example. And then as a community, we then move forwards and we fill this out. We will be doing optimizations as we go forwards. This is just the first incarnation. We'll be working with the community, taking feedback from them, making performance improvements and developer productivity improvements. We're going to add a full kind of RBAC authorization system for enterprise class security. And we're also going to be, again, working with the community to fill out a lot more feature content, including SONiC legacy features, and that also includes FRR, which is a routing stack in the SONiC world. And that, I think, is me.
So I've been talking about the reliability, the manageability. So we community work very hard to provide a very reliable base, and then provide the industry standard command line and REST API for the user to manage the box. Then the question is, what's the next, right? So what other things we want to enable for the community for the SONiC? So one thing is that also our peers. Notice that there may not be a one fit for all north. So because this is open source, everybody can look at source. We publish all the source code, so people can look in, modify the source code, and enable their own scenarios, right? So for their own networks. So one thing is we've been working on with some of the community members is trying to make this SONiC framework to be extensible, so that people can add new features on top of the base SONiC. And today I'm going to talk one of the scenarios, how we work with the partners to enable some of the new scenarios. And one scenario, common scenario, is the layer 4 load balancers. So it's a very typical use cases. You have a web behind a set of dips when there is a web request coming on, so you need to distribute that request to the actual servers to serve the request. So there's a layer 4 load balancers. Currently, the load balancers is there are vendors providing those layer 4 load balancers. It's very critical for the service. The whip coming, so it distributes one of the dips. So one of the problems is that let's say previously, but solving this load balancer is not an easy problem. It requires a lot of data plane functionalities. So, for example, so one of the issues is that you have the web, you do the hash, then you put those requests to one of the server. Right, so all the requests now goes to one server. But your service get popular, you need to add new servers to the deep pool, or your server fails, you need to remove a server from the deep pool. You have to manage the dynamic nature of the deep pools. So here, if you add a new server, then the hash changes. Now all the requests, instead of going to the old server, it goes to a new server, but the new server doesn't have the state, then you end up in a situation that you're not able to service some of the connections. So how do we solve the problem? Basically, the idea is you need some state in the data plane so that when the connection comes, you know this connection belongs to which server, and then you can direct the connection to the server in a consistent way. So I don't want to go to the details, but basically you need some connection in the hardware. Unfortunately, now all the switching ASICs is becoming more and more programmable. They can have a lot of state in the data plane. So making this is a reality. So now the ASIC is very capable of doing such things, and then there are ASIC vendors trying to work hard on this problem and to provide you this load balancer functionalities in their ASIC. And then they need to expose that function to the user, and one of the things is through the SONiC. Because those load balancers usually have networking functions. You need to speak BGPs, other networking protocols. So the question is really, how do we enable the load balancer on SONiC? Basically, there are three parts. Introducing new config DB entries. You need user to control. You need to introduce some schema to allow user to write those things to the config DB so that enable this feature. So the user control part. The second is that extending the switch-there service. So we in the previous slide, we have this all caging, which compiles the application DB into the ASIC DB. That's a compiler. How do you expand the compiler? Because once you get the user input, you need to compile it and actually put those states into the ASIC. So that's the second part. The third part is, sometimes this is new data plane functionalities, means new side features, new side APIs. So how can the vendor extend the side to program those ASICs, the more programmable ASICs? So the first part is more or less easier. So you define the schema in your way. There's a management framework to help you to write the YAML models and define that schema. The second part is that on the left side is a SONiC base. It's a standard SONiC features that it's all on the GitHub, the open sourced. So in the new in this extending mode, the partners does not want to modify the existing SONiC base. They want to introduce a new container that have these functionalities, right? So they write their own load balancer manager. They have their own state, and then they have their own load balancer all caging to translate their config DB, their new defined config DB into ASIC DB. So we allowed that. So they can use our existing Redis infrastructure to do that. And then they can provide your container to download and then provide that functionalities. Then the last part is how to extend the side. Because this is the side is a pipeline, so it defines the existing layer 3 features. But there is also a user pipeline, which define the programmable by the ASIC, but they have these compilers which can automatically generate the new Flex APIs. In this case, it's the load balancer APIs, and expose that API through the side to the user applications. Then the Dockers, that with their new Dockers, can leverage the new APIs and then program those load balancer entry in the ASICs. So then they did a demo You just set up. There's a client. There's a load balancers. There's a controller. So essentially, in this demo, they generate 100K connections per second, and then it refreshing the deep pools. So periodically adding the deeps and then removing the deeps. And here we have a quick demo. So we'll upload the slides so you can view the demo yourselves. I'm running out of time.
Sorry. Yeah. Thanks. Guohan. So this is an open community, open for participation. We welcome your participation about trying the hardware, software, ask questions, or download and deploy that, or also come to the community to review the designs and also filing bugs issues. These are all welcome, and we have a release 4 months. We have a cadence published on our wiki that where are the features, where are the pull requests and the design reviews, that these are all published online, and we are seriously also beef up the documentation. Thanks for the documentation working group that we are adding user guide, CLI dictionary, training videos. In the afternoon, that if you have questions, we are reserving a room in G108. We have the community, hardcore community, developers, contributors, and people who are interested. If you would like to chat more, we will be in that room, G108, from 12 to 2 in that room. If welcome to come to have a chat. With that, I just leave time for one question so that we can give time to the next one. Okay, thanks everyone.